I would like to thank the Fermilab Office of Education and Public Engagement and you for joining us this evening. My name is Janet McKay Galbraith, and I am the Performing Arts Program Manager at Fermilab. Fermilab has a long history of recognizing the synchronicity and interconnectivity between art and science, extending back to our founding director, Dr. Robert Wilson. The ultimate Renaissance man, Wilson believed that the spark of scientific discovery was aided by a rich and diverse life of the mind. An artist and an architect designing much of the artwork you see on the Fermilab campus, as well as Wilson Hall, including Ramsey Auditorium, the in-person home of the Fermilab Arts and Lecture Series. The Artist in Residence program at Fermilab honors Wilson's legacy and connects creative people, scientists and artists, to encourage conversations between these two fields, and then sharing with the public the new artistic vision based on the scientific engagements that have taken place throughout the year. While exploring submissions for the 2020 Artist in Residence program, we were thrilled to see the portfolio of composer David Ibbett. David's long dedication to exploring the intersection of science and music was an undeniable fit for the Fermilab Arts and Lecture Series, and so began this year-long exploration of neutrinos and music composition. David studied at the Clare College, Cambridge, the Guildhall School of Music and Drama, and completed his PhD at the University of Birmingham in the UK. In 2015, he moved from London to the States, and now based in Boston, he directs the Multiverse Concert Series, a project that combines music and science in live performance. In addition to the Fermilab partnership, Multiverse has also had collaborations with MIT, Duke University, the Harvard-Smithsonian Center for Astrophysics, and many more esteemed institutions. Just last month, David and soprano Beth Sterling, who will be joining us shortly, released Octave of Light, a musical exploration of exoplanets presented with the Science Museum of Boston. As part of this inaugural guest composer post, David came to Fermilab in January and spent 3 days visiting the lab, talking to various scientists, attending one of our gallery chamber concert series, and recording Particle of Doubt, his first neutrino-inspired work, at the Icarus experiment on site. He has continually worked throughout the year on various segments of a multi-movement future album of neutrino music. He is joined tonight by Fermilab scientist Bonnie Fleming. We thank her for coming, as well as soprano Beth Sterling. Please welcome our guests.
Good evening. Thank you so much for joining us. My name's David Ibbett, and I'd like to introduce you to tonight's talk, Neutrino Music, a Composer's Journey. So I'm going to start just by introducing myself. I'm a composer with a passion for science. I grew up in the UK. My parents, my mother is a piano teacher, and it was clear at a very early age that I was going to take after her. There I am in Coventry, and that's my old piano, and in fact that piano is still with me. It joined me in my move to America some years ago. And because I picked the music path, I've spent many years studying composition, and during that time, science was an interest at the back of my mind, and it took an interesting turn of events for science to really come to the forefront of my work. But it was always there, thanks to this man, Roger Ibbett, who is a research chemist, my dad, and there he is cooking up some biofuels, experimental fuels at Nottingham University. So I've got music and science in my background, and after I moved to the States, I found a group of people and a recipe for combining the two, and founded Multiverse Concert Series. And we're a project that works with different scientists, different labs from around the country to produce concerts together. I'm thrilled to say that I'm the first guest composer at Fermilab, and that's what tonight's talk is about. I was able to visit the lab in January 2020 and had a whirlwind tour to start my project, and I'd like to relive that tour with you. So come join me. Here I am. It was extremely cold in Illinois, so I didn't stay outside long except for the selfie. And here I am with the other artists in residence. We were all able to visit at the same time, Chris Clapper and Patrick Gallagher. And we saw so many things in those 3 days, and they all stayed with me. In the background there is an incredible piece of machinery in construction. It's one panel of a cube that's going to be an argon detection chamber. And it amazed me just how close they allowed us to get. This is a machine that's going to detect microscopic particle interactions with incredible precision. Yet they let us get, within touching distance. I promise I didn't, but they really trusted us, and we spent time getting close to all sorts of projects underway at the lab, and inspiration began to flow. Here I am. I got to look inside the Tevatron, which was the world's largest particle accelerator that discovered 2 of the known quarks of the standard model. In the workshop with new detectors being constructed. I was allowed to touch things if I was gentle. I was sure that would be okay. And in particular, I enjoyed looking at this SRF cavity that is going to be part of an accelerator. And more about that cavity later in the talk. So I had a fantastic time visiting the lab and spoke with many people. And one man in particular, we had a very long conversation in his office. I'm sure you all know Don Lincoln. He is a prolific science communicator, and he had the unenviable task of sitting down with me, a musician, and explaining the lab's work on neutrinos. I'd been doing my best to educate myself before the trip, but still there was a lot that needed to be said. And this isn't the whole whiteboard, by the way. This is just a section of it. But we spent a number of hours in his office, and gradually the picture started to take shape in my mind. And I've circled what was my first entry point, my first inspiration to the world of neutrinos. If you look, that's a little analogy for neutrino oscillation. So I know we'll have many scientists in the audience tonight, but I wanted to make sure that everybody was able to be immersed in particle physics in the way that I've been lucky to be. So I invited a scientist to join us for the talk. I'm thrilled that she's able to be here. Dr. Bonnie Fleming of Fermilab is going to talk about particles and neutrinos.
Thank you. It's a pleasure to be here. Let me share my screen. And start with who I am. I'm a particle physicist. I've been doing research at Fermilab for the last 20 years, and my research involves at the most fundamental level what particle experimentalists do, which is to break the world down into its tiniest little components. And what we end up with are what we call elementary or fundamental particles, and these are the building blocks of the universe. So we see that these building blocks comprise a very neat picture, which we call the standard model of particle physics. And here's a picture of the standard model, which encompasses 12 building block particles, the 6 quarks and the 6 leptons, and then the force carriers, including the Higgs boson, that help them talk to each other. And of these particles, the ones that I've been studying for now almost 20 years are the neutrinos. And there's 3 different flavors of neutrinos in the lepton family highlighted here. The electron neutrino, which is paired with the familiar electron, the muon neutrino, which is paired with the muon, which is basically a heavy version of the electron, and the tau neutrino paired with the tau. So neutrinos are difficult to study, which is what you should get from this tiny neutrino stuffed animal bandit picture. They're challenging to measure because they have no charge, so they don't do much in particle detectors. And they have tiny mass. For a while, at the beginning of my career, we thought no mass at all. Now we know they do have mass, and they do oscillate, which is a phenomena that we'll talk about a couple different times tonight. And as I said before, they hardly ever interact at all. They are nonetheless a big player in the universe with respect to the rest of ordinary matter. The truth is we know relatively little about the universe. About 70% of it is what we call dark energy. About 25% of it is what we call dark matter. And only about 4% of it is what we call the ordinary matter, the things that we can see that make up the universe. And of that 4%, photons or light particles are the most abundant. That shouldn't surprise you. You can look around and see them all over the place, look up at the stars and see many, many photons. Neutrinos are the second most abundant particle compared to photons. So they permeate the universe. They're everywhere. 3 trillion of them fly through your hand every 3 seconds. They're incredible. And we have asked for a long time, and again, only in the last couple of decades, about their fundamental properties. Do they have mass? And they're at least so tiny that we were unable to measure their absolute mass in the usual way. We had to find a different way to see if some indication that they have mass. And how we did that is to look for a phenomena called neutrino oscillations. In short, neutrino oscillations are when one flavor of neutrino evolves over time or travels over some distance and spontaneously turns into another flavor of neutrino. And you can see that in this diagram. We start with a bunch of muon type neutrinos and we let them evolve over time or travel some distance. And then we measure the same beam to see if any of them have disappeared and turned into another flavor of neutrino, in this case, a tau neutrino. And if we see that phenomena, neutrino oscillations, that tells us that neutrinos mix and have mass. And this sounds sort of crazy, but in fact, you can prove it with a little bit of quantum mechanics, and of course we observe it, and other particles do it too, like the quarks. So how do you wrap your head around what it means that neutrinos have mass? Because they oscillate, then they have mass. A nice analogy, and David will do a better job of describing this than me, but I'll start it, is to think of the neutrinos as different waves. And if the neutrinos have each neutrino has slightly different wavelengths, which is the same as saying slightly different masses, when they mix, we can get a beating effect, which is a suggestion that they're oscillating between their different flavors. So now I'll hand it over to you, David.
So it's been fun putting this little analogy together. Bonnie's going to help me with the terminology. So here's my software that I use to do a lot of my work. This is Ableton Live. And what I've got in here are some synthesizers down at this rack. They're analog synths. They're modeled after a Moog synth, but they produce sine tones, so a very simple waveform. And if you've ever had a hearing test, you might recognize this sound. You hearing that okay, Bonnie? Okay, good.
Yes.
There we go. So we can visualize that. We can visualize the amplitude. So we can see that's not particularly interesting to look at. It has a little bump at the beginning as the note begins, but other than that, the amplitude stays the same. It's constant, like a rectangle. But what I can do is introduce a second sine tone, slightly different tuning to the first. Let's hear that. So that's the phenomenon that musicians know as beating. It's central for tuning a piano. Piano tuners are very good at hearing those slow beats, and it's what gives a honky-tonk piano its character, that extra rhythmic quality to the sound. And it's also great to look at. So let's look at that in amplitude. So we get a lovely pattern of peaks and troughs, and that's our analogy for two neutrino waves of different masses coming in and out of phase and cancelling each other out. And we can see every cycle we come back to where we began. Each cycle is I'm following them along here, but we know there are three. That's three with an asterisk, right, Bonnie? 3 neutrino types? Yeah.
So far, yes.
Yes. So let's have a third one in there. And for the tunings here, so I haven't been able to, we don't know the exact, let me see if I get this right. We don't know the exact masses of the neutrinos, but we do know that 2 of them are close together and 1 of them is further away. That's right, Bonnie?
That's right. We can't actually measure their absolute mass. It's too tiny. But we can see that there is a mass difference between the different neutrinos. And one of those mass difference gaps is small and the other one is larger.
So I've been able to approximate that. But I hope that one day we will be able to get the exact numbers and the exact ratio. You think it's likely in our lifetime, Bonnie?
I hope so.
Me too. And if we get that, then I can update the analogy. But here's what that sounds like. And then we can look at the waveform. So we see that the pattern takes longer to unfold this time. We've got more complex set of oscillations, and I hope that has been illuminating. Thank you very much, Bonnie. So I'm going to continue talking about my residency, and I'll share another slide with you here. Just a second. So this is a poster they have at Fermilab, and I spent a long time staring at it and meditating, and it's all of these mysteries about the neutrino, things we don't know, but might know in the near future thanks to new experiments. So, you know, if this wasn't a sort of a challenge to me, I wanted to see how many of these mysteries I could dig into. And how can I do that? Well, so I'm a composer, and I have various things in my toolbox for engaging with science, sharing science, and trying to illuminate science in a different way. One of my techniques in my toolbox is sonification. It just means representing data as sound. But it's less common than other modes, just because we are primarily visual as humans. We're wired, well, perhaps we will know why with some further study, but it does seem that the large number of data sets, we're used to presenting them as a graph and charts, and that seems to be the default. But there are some scenarios where sound has something to offer, and something that the eye, something that's not readily perceptible with the eye. So here is a famous example of sonification use in science. Now, maybe you will know this experiment. If so, please keep it to yourself. But we can see here is a data set represented with a graph. And it's the same data from 2 different detectors. Have a look. You'll see, you can see what's going on. There's some sort of a pattern there, and maybe there's an event or a couple of events. But let's see to listen to. So, of course, that is the famous LIGO chirp, the Laser Interferometer Gravitational Wave Observatory. And that's the sound of 2 black holes merging out in deep space and sending a gravitational wave predicted by Einstein, but only recently observed. It's very exciting. And this here is LIGO. In its original form, the data is interference pattern between 2 lasers, and it just so happens that representing that pattern as sound, translating it directly into sound, is very illuminating, and you can immediately hear that sharp rise in pitch that we call the chirp, and it tells you that something exciting has happened, and the engineers use that as part of their monitoring to tell them that they picked up an interesting signal. So sonification has a lot of potential. Visual representations of data are not always the most illuminating, And I want to tell you some of the advantages that the ear has over the eye. Standard movie frame rate is 24 frames, and that's enough to fool us that we're seeing something that's really moving. Not so with the ear. The standard sample rate for the sound you're hearing now, actually I think Zoom is even faster, 44,100. I think Zoom is 48,000. But that's several orders of magnitude increase for the frame rate of a movie versus sample rate of sound in order to fool the ear. If we look at frequencies, the eye perceives a small band of the electromagnetic spectrum between 400 790 terahertz. That's about one doubling of the signal. The ear has got a much wider frequency range, 20 to 20,000 hertz, around about 10 doublings or 10 octaves. So if you're trying to fit in frequency data, the ear has something to offer with this wide range. So sonification has a lot of potential, and I've used it in various different projects. As well as being illuminating for science, sonification can become music. Because we emphasize the visual, sound has a unique quality to affect us in a subconscious way. And if you weave a sonification into a musical framework, into a composition, you can bring the science into the emotional space and communicate something about its meaning, the deeper meaning of the experiment, the hopes and dreams of the people who are doing the work, and what we might learn about humanity and the universe. So I want to talk about a piece. This is one that went out earlier this year, Particle of Doubt, and it's sort of a trailer for the project as a whole. It's based on some data. This is a neutrino oscillation simulation, similar to what we showed you earlier. But here the waves aren't summed together. You see them separately. This is the probability of finding any of the three neutrino types as they travel through space. And they travel quite a long way. And at any point, if you measure along, if you pick a point along the x-axis, the total probability is 1. So at the beginning, you've got a 100% chance of it being an electron neutrino. But as you get towards the middle, you're likely to find any of the three kinds. And at some point, you take a measurement, and the wave function, the quantum mechanical wave function, collapses, and then you find out what you had. So this is it's beautiful to look at, and there are some underlying patterns. But I wanted to see, what can music do? Can it help us not just to see, but experience the data and its meaning in a more direct way? I wanted to communicate the grand scale and the distance. So these are particles moving at almost the speed of light over vast distances across state borders in some cases. More about that later. The fascinating and beautiful way that they interplay with each other, and they cancel each other out, and the underlying mysteries and ramifications of them, as a particularly interesting theory called leptogenesis, which is trying to explain why our universe is dominated by matter. We wonder why matter and antimatter were not created in equal amounts at the beginning of the universe. If they had been, they would have annihilated and we would have nothing, but we know that's not the case. Matter won out, and perhaps the leptogenesis theory tells us that it was neutrinos that had something to do with this imbalance that led to us being here, and studying neutrino oscillation might give us shed some light on that theory. So how do I bring that into the sonification world and the music world? Well, it's a simple beginning, mapping probability to pitch. And I arrive at this. So I brought in some instruments at this point. So I'm classically trained, and I love the strings. My wife's a violinist. So she got to be the electron neutrino. The viola gets to be the muon neutrino, and the cello gets to be the tau neutrino. And strings are really wonderful. They have such a wide range, and they can get across this huge scale of the oscillations. So unlike the graph, which is very smooth, I chose to do some rounding. And that's something I often do in music to make a balance between the fine grain of the data and bringing it into a familiar musical space. So I chose a well-known scale, the Dorian mode. It's very old scale. You can trace it back to ancient Greece. And it's associated with urgency and drive. And I really wanted to weave that into the piece. And finally, I thought I would introduce a little bit of instability in the rhythm, a sense of swing. So that's how the sonification came to be. Now this is pre-composition, but let me show that to you. So producing that was really the beginning of my creative process. I mean, sonifications are interesting on their own. They can tell you something about the data and they can bring in a certain amount of emotion and meaning. But I like to go further and bring the sonification into a larger musical framework. And that's where my longtime collaborator, Beth Sterling, comes in. And she sings the main lyrical melody of this song, which is all about the mass of neutrinos, which they shouldn't have according to the standard model. They change in mysterious ways, and they might tell us where we came from, and we're going to learn a lot in coming years. And well, I certainly want to be there as we learn these things. So I'll now share that piece with you, Particle of Doubt. Just a second here. Hello again. So I want to say that that is a slice of what will be a larger song in the future. We used it as a trailer for the project, but there will be more of it when the full album comes out next year. So I want to talk to you now about another project that uses sonification, and I hope I'll get to use this technique with neutrinos in the near future. So this is a project, Octave of Light, and Janet mentioned that it's an album that came out this year, and it uses a different method in order to explore astrophysics through music. A way of using harmonies to listen to the sound of exoplanets. It's a collaboration with Roy Gould of the Harvard-Smithsonian Center for astrophysics, and he helped me to learn about exoplanets and exoplanet spectroscopy and the way that exoplanets are detected. He has a wonderful book, The Universe in Creation, explaining just how finely tuned the universe is for life, and how many of the physical laws are on our side for giving rise to living creatures. So the basic science here is the way that exoplanets are detected by something called the transit method. As the planet passes in front of the star, it causes its light to dip over a period of time, and we're able to not only detect that light and therefore deduce that a planet is there, but we can also analyze that light and break it apart with a prism to learn the color of the planet. Now, I say color, but these are colors that are spread way outside what the eye can see, and in a much wider range that the eye could ever see. Even if you brought it out of the infrared into visual range, you can't fit the entire spectrum in. So this is where the ear can help. If you remember, the ear has a much wider range of frequencies. So I wanted to see if we could listen to these exoplanet spectra by mapping the wavelengths and frequencies to musical notes. So this is one of the first ones I did, WASP 17b, exoplanet. So you'll see it's the other way around. They like to represent it wavelength going up, which means pitch going down. And the wonderful thing about this data is it not only tells us the color of the planet, but you can associate the colors with particular molecules in the planet's atmosphere. If you compare the spectrum here with experiments in the lab, you can tell that the largest dip is to do with the presence of sodium. We can track another line to the presence of potassium, and 3 lines to the presence of water. So we know that this is a planet with sodium, potassium, and water vapor. Perhaps you want to know what that sounds like. So I'm sure you have some questions. There are a few steps. Obviously, there's the rounding to the chromatic scale, and shifting down into the audible range, about 40 octaves actually, because light waves are so much faster. But the key thing is that the relationships between the dips are preserved. So a fifth is a fifth, an octave is an octave. And that's something that was important to preserve in the method. And I'd be interested to know in the questions how that chord came across. To me, it has a slightly jazzy or maybe an air of angst to it. So it is woven into a song on that album, Wanderers, about the wanderlust that we have of knowing that we're in a universe rich with planets. We know of over 4,000 exoplanets beyond Earth, and yet we will never go in our lifetimes, perhaps someday. Here is a little segment of the piece that ultimately became. So I'd like to share with you a full composition from that project. This is a different one called Water Romanza, all about the water vapor spectrum. Just bear with me a moment. This also features Beth Sterling. Water Romanza. Just want to give credit to the Boston Museum of Science planetarium team who produced those incredible visualizations for the project. Incredibly grateful for them working with Multiverse during the lockdown and helping us to continue to reach people even in these difficult times. So I promised a world premiere for this event, and we're almost there. But I want to hand back to Bonnie now, because she's going to introduce the MicroBooNE experiment, which has become very important to me these last few months.
Thank you, David. Let me share my screen. So I'm going to say a few words first about how neutrinos interact and then how we see them and what we're trying to see in the MicroBooNE detector. First, seeing neutrinos is hard. I mentioned that already. They're all around us, but they mostly pass right through us. The average neutrino will pass through 200 Earths stacked on top of each other before having a significant chance of actually hitting something. But so to do neutrino physics, you need lots of neutrinos, massive particle detectors like the DUNE detector that you saw in the video earlier, and ideally really specialized detectors, really precision detectors that can see neutrinos very well. And just to say, detectors don't actually see the neutrinos. Neutrinos are neutral particles, no charge, so they don't actually emit other charge or light in a detector. We really only see them in a detector when they hit something in the detector and turn into charged particles. And here you can see an actual neutrino interaction in MicroBooNE, the liquid argon time projection chamber that is MicroBooNE. And the neutrino sneaks in from the left here, doing nothing in the detector, and it hits the argon and turns into a bunch of other particles that we actually see. So this kind of detector harkens back to the bubble chamber detectors from the 1970s. There's many beautiful images of particles forming bubble tracks in bubble chamber detectors. And they were beautiful detectors, but constrained by size. Some of the biggest of which is the 15-foot bubble chamber. There's a picture of it to the right here. So in order to go to much larger detectors, which you need to see lots of neutrinos, we had to go to less precise detectors, which you can see in the lower right. If we were actually at Fermilab, I would tell you that this detector is so massive, this is the Super Kamiokande detector from Japan, that the Fermilab 15-story high-rise can actually fit inside this detector. So with MicroBooNE, we're on a path to both be able to build those really large detectors in the future, but using a precision technology, a liquid argon TPC, which has images like the bubble chamber detector. So it's a modern version of the bubble chamber. So here's that particle interaction again. Neutrinos hit the argon and other particles are produced. And how these particle tracks look tell us what kinds of particles they are. Electrons and photons produce these showers. Muons and protons and pions produce tracks. Protons, by contrast to muons, produce these dark red tracks compared to the lighter tracks because they deposit more energy as they pass. So we see and identify these particles in the detector because of the tracks of ionization electrons that they leave as they pass through the detector. And we work backwards to figure out what kind of neutrino it was. I mentioned these detectors in the future will be absolutely massive. For now, we've built MicroBooNE, which has been running since 2015 on site at Fermilab right here, near to the high rise. It's about the size of a school bus. You can see here us driving it across site before installing it in the neutrino beam at Fermilab, and then the inside of the detector, which is a bit like the Icarus picture that David was standing in front of in the early pictures. It shows the inner layers that actually read out those beautiful tracks. So what will we do on MicroBooNE? We're looking for electron neutrinos in a primarily muon neutrino beam that's created for us by the Fermilab Accelerator Complex. If we see an excess of electron neutrinos, more than we expect, meaning the muon neutrinos travel over 500 meters from where they're created to our detector, and we look for electron neutrinos popping up in the beam. And if we see a bunch of them, it's an indication that we have a new kind of neutrino, which people refer to as a sterile neutrino or something else really weird. So That's the main goal of the MicroBooNE experiment. In addition to that, we'll try to understand all the ways that neutrinos can interact in a liquid argon detector en route to understanding how this technology works so we can build this kind of detector on the scale that we need for the DUNE experiment. I'm going to pass it back to you now, David.
Thank you so much, Bonnie. So I must confess, I saw a lot of things on my Fermilab tour, but I wasn't able to see the school bus itself. But what I did see was these amazing event displays that crop up in real time in the control room. And I was in there just looking at one of the, actually an example of scintillating light fibers, which have also kind of been on my mind. But I saw one out the corner of my eye and managed to chat to the engineer, and he was very gracious to take time out of his work to explain to me a bit about how you could not only see the particles, but you could really identify what was what. And after speaking with Bonnie and some of the other scientists, I've been able to learn about the experiment. So MicroBooNE, what Bonnie has shown you, she showed you one of the event displays. And if I'm correct, Bonnie can chime in with my language. What that shows is an afterglow of a particle collision. So not the collision itself, but the entire sequence of events sort of frozen and superimposed, sort of like the sun leaving an imprint on your retina. And then to get the chain of events, which takes place in an absolutely infinitesimally small slice of time, you have to deduce what happened first, which particle hit which one. And multiple detection methods are used to figure that out, plus the laws of physics as we know them. And I wanted to know, could sonification allow us to see, hear, and experience one of these particle events as it unfolded in time? But could music evoke the hunt for the electromagnetic excess and a possible fourth kind of neutrino, the sterile neutrino? So I had to pick one of the event displays to be the basis of my piece, or to start with. And there are so many gorgeous images available for the public to see on the MicroBooNE website. But I hope you'll agree that this is a particularly fine one. You can see quite clearly on the left there where the neutrino impacted with the argon, which sends protons flying off, and then this gorgeous shower created by an electron ionizing the fluid. And so I had to decide, how was I going to turn this into music? And because I was focused on collisions and events, I started by tagging important points within the image. And I tried a few different ways, but in the end, too many just made for chaos, and not enough was kind of dull. So this wasn't the first set of points, but these are events where there's a spike in heat, or a particle terminates or impacts. So originally, I was just going to play through these points from left to right, but I was chatting with my brother, David Ibbett, who's an animator, and he was able to put together something a bit better, an artistic imagining of how this particle event might have occurred in a small fraction of time. And we get to watch it in slow motion, and then with a sonification. It's a simple method. The higher on the screen corresponds to a higher note for the piano. So I'll show that to you. So very much like Particle of Doubt, that was the creation of my sonification, but the beginning of my compositional process. And I wanted to do something I haven't done before, which is just show you a little bit of what happens next. So I'm going to load up my actual composition set here. So I'm a classically trained composer, but I am passionate about new technology and electronics. So here is my software again, Ableton Live. And you'll see this box here. This is the sonification in MIDI form. And each of these is one of the points. We can hear that. And there are lots of other elements, as you'll see, and I'll sort of explain the journey. So beginning with this sonification data, some of the notes are rounded to a full chromatic scale, and others I decided that I wanted to go for a major tonality to convey the excitement and drive. So there are points where it's rounded to A major, but I can show you. Here's my, let's see, that's so major tonality and full chromatic. You can see, depending on, I was choosing certain more chaotic moments to be chromatic. I decided early on that I wanted to work with Beth again for this piece. And I wanted to bring in her voice as an anchor. And the first thing was creating a cantus firmus for the piece. That's a term from choral music way back in the Renaissance. And it's a term for a slow-moving melody with the core message. It would originally have been a liturgical piece. But in this case, she's very slowly singing the names of the particles as they come up. So you can hear her. And she's picking out notes from the sonification. So her melody is directly drawn from the sonification. Just certain notes are held as the piano moves underneath. And then finally, I wanted to harmonize my melody. So I begin with A major. Dominant. Minor. Dominant. High tone. Little reference to Tristan and Isolde there, if you know that one. So there's melody, there's harmony. Final ingredient, I'm a big fan of rhythm, and I wanted to show the drive and the fact that this is a hunt for particles that is currently underway. So I took those harmonies and arranged them for strings in a beating rhythm, and hopefully we'll be able to record some real strings as my virtual strings. And eventually, no. Melody. I really let it go at that point and started bringing in a lot of other instruments, orchestral, synthesizers. And as usually happens, after an initial investment at the beginning, the composition starts to gain a life of its own. And that's what became the piece MicroBooNE. So we're going to share it with you now, the full composition with Beth singing. It's almost live. We recorded it just a couple of days ago. I hope you'll forgive we're not here in person with you. But I'm now excited to share the first performance of MicroBooNE. Thank you so much. We finished that today, so hot off the press, so to speak. I think we just have a minute. I wanted Bonnie to say a little bit about MicroBooNE and where we are right now with this experiment.
Thank you. That was really, really wonderful to hear, David. That was wonderful. I will only take a minute. I would love to follow that with whether or not we actually see the electromagnetic excess, but we don't know yet. We're almost to our first results of whether or not we see this little bump of events or not, which would indicate new physics. We're doing what's called a blind analysis, so we don't know the answer either. We've only looked at about 5% of the data. And if we do see this little electromagnetic excess that suggests electron neutrinos, then that's new physics, which is really exciting. And I'll end with one of my favorite event displays. You've shown us so many tonight. A main goal of MicroBooNE is to develop this beautiful technology for future detectors. And now when I say beautiful, I say both looks beautiful and sounds beautiful.
Well, thank you so much, Bonnie. So I'll just wrap up before our Q&A. Oh, there we go. So this is going to be a full album of neutrino music. A couple of compositions in, but my mind is full of the possibilities. And well, I definitely won't be able to fit it all in, but like Octave of Light, it'll be a full album. I want to work, in addition to what I've already engaged with, supernova neutrinos, more about the LINAC beam at Fermilab, and of course, DOONE, this new groundbreaking experiment of huge scale and distance that Fermilab is building. I hope to see the caverns and the detector, and yeah, it's going to be a wonderful ride. But if you have thoughts about what would translate best into music from the lab's research, I really want to hear from you. So put in the Q&A. We're going to do studio recordings and live performance of this music as soon as we're able. But for now, I've made it available for anybody. It's free. You can download the music and in higher quality and watch the video at neutrinomusic.com. So would love to know what you think. And I'll be putting the other pieces are on there, and I'll be putting other compositions there as the project evolves. And that's part of Multiverse Concert Series, the project that I'm directing. And we have events next year online I'd love to see you at. So that concludes my talk. And I think Janet is going to introduce the question and answer.
I'm back. Yeah, thank you, David, so much. And Beth and Bonnie, what an incredible evening of music. I am so thrilled to have music come back. And this, I can't imagine a better way to have that all happen. So we're thrilled to have you here. I do have some questions. One of the first, and I think it was referring to the new piece, and I think I know exactly where they were talking about. The question was, why did you switch from major to minor in the piece? And I think that my guess is that showed up right about the time it happened in the soprano line.
Oh, in MicroBooNE.
Yeah.
Right. You know, at this point, there's a mixture. I'm starting to get into, let my intuition, but take over. But that's the point where the electron leaves the arc of the protons and starts to escape on its own. So it's a lift up in the pitch, but it's moving to the minor harmony, which is part of the scale. So perhaps the electron is leaving home. I'll go back and check that. Actually, it's a very good question.
Okay. Sonification is very cool as a way to connect data to the public, such as your amazing composition and what LIGO has done. My question is, are scientists using sonification in their data analysis in ways analogous to what they do visually? If not, is there an opportunity to train scientists to see data orally as a way to gain insight?
Absolutely. I mean, I'm really interested in existing uses of sonification, and you know, LIGO is probably the most famous with that chirp, but there are some others that I've come across, scientists who just find that listening to the data is better. You immediately know what's going on. You can listen to the sound of a Drosophila neuron firing. There's a whole community of people that plug electrodes into the brains of insects and listen to them firing, and you can immediately tell when that neuron has started firing. So it just so happens that that scenario is one where sound is very good, and there must be plenty more out there, but perhaps scientists are not always aware that the sound might be useful, and there are opportunities to try that haven't been tried. So I would love to help. So yes, if you're working on a project and interested in some tools for sonification, do let me know. I just want to say that Beth, our singer, has joined us for the Q&A, and she's worked incredibly hard to bring this music to life. It wouldn't be anything without her. So please direct questions to her.
I have a question for Beth next. So perfect lead in. So Beth, how do you approach some of this new music that is all science-based, as opposed to the way you would approach any other classical singing? Do you have the same approach to that?
Yeah, that's a good question. I would say in order to make it a good sung performance and to just make it an artistic performance in general, I kind of have to translate that science into something emotional. David's done some of that for me already. Usually when he hands me the piece, he gives me a little bit of background information about what exactly he's going for. So for the piece that we just premiered, that was kind of delivered to me as if it were a love song or a breakup song. So I went in that direction for my performance. For something like Octave of Light and any of the pieces that I've collaborated with him on, I try to think of it like I'm learning all of this new information about neutrinos and about science and exoplanets and everything myself. And there's this just incredible sense of wonder about all of this information that's out there for me. So I try to encapsulate that and put that into the performance as well.
So David, how do you decide on what tonality and meter to use when you're looking at an image and you're deciding to sonify it?
That's a good question. I mean, I like to combine the familiar with these fantastical science experiments. So, for every composition, there has to be a certain amount of wonder and discovery. Why do it otherwise? So the science brings so much of that, and sonifying data, you're usually going to get something that sounds odd and different. If it doesn't, then maybe you didn't. Maybe your method wasn't that good. But if the data is meaningful, it should be striking in some way, and therefore I might use tonality as a way to ground it. And I love familiar harmony. We have so many associations with major and minor, and combined with rhythm. Major can suggest excitement. I mean, there's so much excitement and drive to all of these experiments that are busily being built right now. So that, I think, for this project, those are the kinds of musical scales I'm looking for, things that suggest great work underway. I think for the particle of doubt, that one ended up with more of an urgent tone, and I think it's sort of existential doubt, I think, is underneath that. So, figuring out what the origin of matter, seems to be almost beyond ken, but perhaps not quite. But then MicroBooNE is just these joyful images coming in, and major tonality is used for that, but there are some other chromatic shifts in it to do with the questions. So you're right. I'd love to think more about that, actually.
I have one more question and then one more suggestion. So I'll start with the question and we can end with the suggestion from a longtime friend of Fermilab. Actually, a long time, more than a friend of Fermilab, part of Fermilab. But the first one is, the question is, scientists often have trouble communicating the drama of basic research. How exciting it can be to discover the mysteries of the universe in a way most people understand. How do you hope your work will express that drama to a wider audience? Do you see it as a learning tool? Excellent question.
Yes, I hope so. I hope that bringing these ideas into music can make them more direct. if you can hear it and you can experience it as well as know it, it's just more ways to come at the data and come at the knowledge. And I hope that it can be a way to entice people into science, and the small amount of science that I'm able to weave into the music can hopefully lead people into wanting to dig in more and start asking the questions, well, either being scientists or musicians or both. So that's very much what I hope to do, and be doing more of in the future.
I think you've learned more than a small amount of science. You've jumped in with both feet. And finally, a suggestion: atoms emit spectral lines in the optical band, several lines like a chord if sonified. So stars with different compositions are singing different chords. It's such a romantic thought. That could be a fun project. That is a suggestion from Mike Albro. So
that sounds great. Yeah, Mike, send me an email. Let's chat.
So there's the next, there's the next project for you. Well, thank you so much. Thank you to the audience for coming. Beth, we were so happy to have you. Bonnie, thank you again. And David, it is lovely. I wish you could have come back to Fermilab and visited, a couple more times, but you have certainly made the most of the time you've spent there, and we'll just have to put that off for a future date and have another concert when we can do it live at Fermilab Arts and Lectures. Thanks for coming, everyone, and have a good evening.
Thank you.
Thank you.